Now, Tomas is going to talk about almost quantum correlations and Pecker's principle. So, okay.
Thank you. So, first of all, in the interest of diversity of introductions, I have to thank everyone involved in organizing this amazing conference. But yeah, jokes aside, definitely it's been one of the better conferences I have attended so far. In this talk, as has been pointed out, I want to tell you about almost quantum correlations and how they are inconsistent with Pecker's principle. So there's two things I have to unpack: the almost quantum correlations and the Pecker's principle. But before I do that, let me mention what's the general motivation for this work. So the broad question we are asking is, can we uniquely identify the set of quantum correlations? That means the possible outcomes of quantum experiments or the possible statistics you can get out of quantum experiments from some reasonably nice principles. I will not dwell on what nice means. That may depend on what kind of principles you like, but that's the kind of broad question. This question has faced, like, people who have asked and tackled this question have faced challenges, and one of those challenges is that many of the principles that people come up with to try to get to the bottom of this have the property that they allow for a larger set of possible correlations than the quantum correlations, and this larger set of correlations has been dubbed almost quantum correlations for the first time in this paper from 2015. So in this talk, what I would like to tell you is a possible avenue for a solution around this challenge, and that's namely that Pecker's principle actually rules out the almost quantum correlations in its full form as has been defined and then extended later on. So what is Pecker's principle? Well, when in Pecker's own words, what he said, if you have several questions and you can answer any two of them jointly, then you can also answer all of the questions. So this is a little bit vague, and I will expand on that a little bit later on throughout the talk. But now let's look at the outline of how we will get there. So first I will go through some definitions so that we know what we are talking about. And afterwards I will go through the argument, the main argument. First of all, I will show that the Pecker's principle implies that in certain experimental scenarios, there can only be classical outcome statistics. And by classical, here I mean outcome statistics or correlations that can be explained by a non-contextual hidden variable model. Then we will observe, or we have observed, that there are some almost quantum models in these kind of experimental scenarios, in some of them, which are nevertheless not classical in the sense that they do not admit a non-contextual hidden variable model. And as a consequence of these observations, we conclude that the Pecker's principle that measurements which satisfy Pecker's principle cannot possibly generate all the almost quantum correlations. So let's, if there are no questions about this, so let's delve into the definitions. So first of all, I need the notion of compatibility of measurements. We have already seen this from Leandro. I will say that measurements A1 through AN are compatible or jointly measurable if there exists some mother measurement that can simulate all of these single measurements by some stochastic post-processing. And for example, in quantum theory, the projective measurements, what this means for projective measurements is that they have to be commutative. That's not the case for POVMs, but that's what it means. And for our purposes, one of the most important takeaways from this definition is that whenever we have some set of compatible measurements, then the marginal statistics of the outcomes of these measurements have to admit a joint probability distribution. And this is just because there is the matter measurement which has certain distribution of its outcomes. Now, the Specker's principle talks about measurements and compatibility. So how we will attack this this incompatibility between the principle and the correlations is by studying contextuality scenarios, and in particular contextuality scenarios whereby we have measurements. So these are M1, M2, M3, and they have certain compatibility relations among them. So in this case, this is an example of a compatibility hypergraph, which is called Specker's triangle, by the way. And in this case, we have 3 measurements. And just for simplicity, we will consider each of them to have 2 outcomes. And any pair of these 2 measurements is compatible, which is denoted by these hyper edges. In this case, they are just edges. They just contain 2 measurements. Now, for each of these pairs of measurements that we can perform, we have 4 outcomes, because each M1, M2, M3 have 2 outcomes. So in total, there's 12 possible events. And this, as I said, is for each choice of the 2 measurements, we have 4 events. And now these events we can again draw in a hypergraph, which is this events-based hypergraph, which is what Ravi was talking about just a few minutes ago. And this is a more complicated hypergraph. I will not go into all the details, but what the events-based hypergraph corresponds to, it comes from the compatibility hypergraph. So in this case, they describe the same scenario. It's just the vertices and the edges represent different things. So in the events-based hypergraph, what I wanted to say, yes, is that any of these sausages which enclose certain sets of events, what they mean is that the probabilities of the events have to add up to 1. So in some sense, those sausages correspond to some choices of measurements, a complete measurement, so to say. Then the objects of study on these hypergraphs are probabilistic models, assignments of probabilities to each of the events. So that's also what Ravi was talking about. And they have to satisfy this requirement of completeness for each of the hyperedges. So the probabilities of vertices or events over each of the hyperedges have to add up to 1. And so that's what we would call a probabilistic model. And now, in order to compare different theories and their predictions, we will coarse grain the information that a certain theory has. So for each of these hypergraphs, we can consider the set of all possible probabilistic models that are predicted by this theory. And likewise, we can also compare different assumptions on these theories by looking at what constraints this assumption places on the set of all probabilistic models. So one assumption is the assumption of non-contextual hidden variable models, and that's what we would call classical probabilistic models. So classical probabilistic models are ones which are just convex combinations of assigning 0 or 1s to the various events, the various outcomes of measurements. Then we can have quantum models, and the set of all, or the quantum model, probabilistic model, is one that there is some quantum state on some Hilbert space. There is a family of projectors. So there's one projector for each of these events. And they have to satisfy the normalization condition. So the projectors sum up to identity. And furthermore, the probabilities of that quantum probabilistic model are just given by the Born rule. And now finally, we get to the definition of almost quantum models. So almost quantum models are almost like quantum, and they are defined like this. So again, there is some quantum state, there is some Hilbert space, there is some set of projectors, one for each of the events. However, now we don't require that the projectors sum up to identity. They can be subunital. So here, this ordering is just the lower ordering. And again, we have to require that the probabilities are given by the Born rule with respect to these subunital projectors. So this is what almost quantum models is. And you can see that the almost quantum models, the set of almost quantum models is going to be strictly or larger than the quantum set. It's not necessarily clear when is it strictly larger. And so having defined all this, we can now move on to the Specker's principle. I will slightly restate it so that it is more, so that it's easier to analyze it through these contextuality scenarios. So we can also state it like this. If in every set of measurements for which every pair of those measurements is compatible, all the measurements are compatible, we would say that such a theory with such measurements satisfies Specker's principle. There's no water. Okay. So Specker's principle, as stated here, it pertains to measurements. So that would be the structure of the theory. But as I've defined here, almost quantum correlations, they don't really care about the theory necessarily explicitly. They only relate to correlations or outcome statistics of measurements. So there is a statement, consistent exclusivity, which can be applied to correlations. And Ravi mentioned it. You can have models which satisfy consistent exclusivity. And what consistent exclusivity says is that whenever you have a set of events such that each pair is exclusive meaning that only one of the two can happen at the same time, then the sum of the probabilities of all these different events which are pairwise exclusive cannot exceed 1. Now, it turns out that Specker's principle actually implies consistent exclusivity. And how much time do I have? 10 minutes. Okay, so I will outline the argument for why Specker's principle actually implies consistent exclusivity at the level of correlations. So let's go through that. Here is an example of some events-based hypergraph. So it looks like the Specker's triangle, but actually it's not. So here the vertices are events. What we want to focus on are events V1, V2, and V3. So those are our set of events which are pairwise exclusive. So you see each of them is contained in some measurement. And by assumption, different outcomes of measurements are exclusive. Only one of them can happen. And so now in this events-based hypergraph, we have several measurements. There's M12 is a measurement, so that's this one. It has outcomes V1, V2, and W3, which is some other outcome. We may not know what it is, but there's some other outcome. And after observing that this is a possible measurement, we can also consider coarse grainings of these measurements. So if we coarse grain V2 and W3, we get a measurement that I called M1. So M1 is a measurement, one of whose outcomes is V1, and the other outcome is just the complement. And similarly, we can get the same measurement by taking this left M1 free, say, and coarse graining V2 and V3 and W2. That's right. And similarly, we get a measurement M2 by coarse graining, or M3, and what we get is three measurements: M1, M2, M3, just like up here. And these three measurements will have this compatibility structure. So this is actually the Specher's triangle now. This is compatibility hypergraph. And now, by applying Specher's principle, we can conclude that these three measurements, they are pairwise compatible. So each pair of these two measurements is compatible. By the way, if that wasn't clear, the joint measurement for say M1 and M2 here is just M12, because you can post-process that one to get M1 and M2. So that's why they're pairwise compatible. And now, because of Specher's principle, which remember said pairwise compatibility implies global compatibility, we can actually say, oh, that there's a global matter measurement for all three of these. And following on, there must be some measurement, this M13, such that some of its outcomes correspond to V1, V2, and V3, the original ones we started with. And since the outcomes of this measurement have to be normalized, we get that the probabilities of V1, V2, and V3 add up to at most 1. So that's why Specher's principle implies consistent exclusivity. And there's a slew of other consequences of Specher's principle that you can come up with that apply at the level of correlations. Here I will mention one of them, which will be important for us. It's called pairwise sufficiency. And pairwise sufficiency, or as we called it in the article, pairwise sufficiency for probabilistic models, is kind of a direct consequence of Specher's principle if you look at it. It says that the probabilistic models generated by sets of measurements which are pairwise compatible have to be classical. So this just follows from the observation that whenever we have set of measurements which are all compatible, then they can only generate classical probabilistic models. So here, Specher's principle implies pairwise sufficiency fairly directly. Now, as it turns out, as I was talking about this challenge to identifying principles, picking out quantum correlations, it turns out that consistent exclusivity is one of those principles that are challenged by this, because they are satisfied by almost quantum probabilistic models. And this has been shown, I think, first by Miguel Navasquez for the case of Bell scenarios, and then also in this paper for the case of general contextuality scenarios. And so this doesn't really help us. It just says, yeah, there's a consequence of Specher's principle, which is satisfied by almost quantum models. Yep, that's not helping. However, we have identified this scenario, which contains 4 measurements. Each pair is compatible. So this is, again, compatibility hypergraph. And it turns out that in this experimental scenario, there are almost quantum models which are outside of the classical polytope. So there are almost quantum models for this scenario if you translate it to the events-based hypergraph version, which do not admit a non-contextual hidden variable model. So we can conclude that the pairwise sufficiency as a constraint at the level of correlation is not satisfied by all almost quantum probabilistic models. And as a consequence, going up, that means a contradiction between Specker's principle and almost quantum correlations. But it's a bit subtle, right? Because almost quantum correlations, they really talk about correlations. There's not necessarily an almost quantum theory which you could apply Specker's principle to. So the kind of more precise statement would be something like this, that measurements that satisfy Specker's principle, as stated before, cannot generate the set of almost quantum correlations in its entirety. And that will apply not just to almost quantum theory, if there is one, but also any other theory which which can possibly generate almost quantum correlations with some set of measurements within that theory. So with that, I would like to conclude. First of all, I have tried to argue that Specker's principle, or maybe some consequence of Specker's principle, be it for measurements or the correlations, could single out the set of quantum correlations. It's not clear what is the actual set of correlations that's implied by requiring the Specker's principle holds. It could be definitely bigger than quantum correlations. It cannot be smaller because we know that projective measurements in quantum theory, which are those that, as we've discussed, the events-based hypergraph framework applies to, we have required them to be projectors. So quantum theory satisfies Specker's principle. We don't know what is the set of correlations implied by requiring Specker's principle necessarily. Now, there's another thing, which is what I was talking about here, is that, oh, sorry, that was very quick. If in any theory there are some measurements which are capable of generating all of these almost quantum correlations, then necessarily some measurements in this set have to violate Specker's principle, and that's just a direct consequence of all this. And in particular, if we have this set of measurements in some theory which we would call sharp measurements, and we would want them to reproduce quantum correlations, then some of these sharp measurements have to violate Specker's principle, which is, for example, in contradiction with some notions of sharpness which have been proposed. So there are some notions of sharpness in general probabilistic theories which, by this argument, cannot generate almost quantum correlations, and that could be a good thing if you don't want to generate almost quantum correlations, I guess. So thank you.
Thank you, Tomas. So, questions? Questions? Okay, sure.
Maybe it's just like a subjective question, really, which is how likely do you think it is that Specker's principle could actually single out? I mean, what you're saying is that you cannot rule out that that's a possibility, but what would be your guess?
I would guess it doesn't, but I don't really have any numerical evidence to base that claim on. So I don't know. But I don't think so.
Okay, more questions? No, so let's thank Tomas again.
Thanks.